Good morning. My name is Blandino. This presentation is about the research that we have done for this topic, a comparative evaluation of parallel programming Python tools for particle in cell on symmetric multiprocessors. Particle in cell is a computational method to study multiple physics applications like fluid mechanics, plasma, cosmology. The first particle in cell simulations use less than 1,000 particles, but simulations nowadays use hundreds of thousands or even millions of particles, and this represents a challenge for computer systems. Large particle in cell simulations require the usage of optimized of supercomputers with optimized code in programming languages like Fortran, C, or C++. The increasing popularity of Python in the recent years has been adopted by the scientific community to run simulations. There have been a development of multiple different tools for this. Some of these tools are intended for parallel programming. This article is about 3 parallel programming Python tools used on, these are tested on 2 multiprocessors, making a comparative analysis from a high-performance computing perspective using a particle in cell code as a benchmark. The main objective of the particle in cell code is to simulate the motion of particles in the interaction of position and velocity with self-induced and external electromagnetic fields. In order to do this, particle in cell uses a grid from where the position of the particle is interpolated. Particle in cell uses a loop with 4 different operations. The scatter operation basically interpolates the position and velocity of the particle and then projects the charge and current density into the grid. In the solve operation, with all of these changes on current density and charge, you solve Maxwell equations in order to get new values for electromagnetic fields. In the gather operation, all these new values of electromagnetic fields are projected back into the particle, and this projection creates an effect on the particle that gets a movement and a new position with a new velocity, and then you go back to the scatter operation, and that's what the particle in cell loop is about. Python is an open source programming language. As I was mentioning, it is easy to learn. It has earned a lot of popularity in the last 20 years. And with it has come the development of different tools like SciPy and NumPy, which are mainly used for scientific simulation, numerical operations. There is also Dask and Pandas, which is used for data science. These are able to handle big data sets and perform operations on this. And there's also scikit-learn, which is used for machine learning, and there are other different tools which are used for parallel programming, like Numba, multiprocessing, TorquePy, and PyMP. Multiprocessing is a library that supports spanning processes with an API similar to other threading modules. The multiprocessing library avoids the limitation of Python build and uses subprocesses instead of threads. This is how it is possible to perform, to use multiple forms. There are 2 main ways to use parallelism in multiprocessing, by using pool and by using process. Pool is intended so when you have big input values, you split them into different chunks and you work based on this on different cores. And with process, expands and creates objects and then calls them with a start and join methods. PyMP is built based on top of multiprocessing. It has a very similar programming style like OpenMP. It doesn't use, Python doesn't allow pragma, so you have to use language constructs for this. And the main ways to use parallelism is through the with instruction, which creates like the parallel context. The range instruction is using for loops in order to split the data across cores. And you also have to use shared arrays in order to handle better the data. TorPy is an open source library developed by IBM. It was created to support task and data parallelism on shared and distributed memory architectures. It uses MPI internally. This is transparent to the user, but actually the user can explicitly use certain MPI operations. It provides support for nested loops, for map functions, for submit and wait functions, and it's important to highlight that an start function is required in the main flow in order to initialize like all the parallel context. Python Pig, this was the code that we used as benchmark in this case. It was initially developed by Dominic Stanson, which is a Polish researcher. Basically, he created a sequential code in Python and in C++ to evaluate the performance. It uses Numba to make optimization of the code, but it's not using the parallel operations. And in this case, Python Pig is extended with 3 different tools to evaluate the performance of these tools. The Python Pig structure is based on some configuration scripts with different input values and parameters. These are passed into some config files which understand and handle everything with the flow related there. And basically, we use 3 different files, which are simulation, species, and grid. Simulation handles everything related with input and data, and also the simulation flow itself. The species handles everything related with the particles and all the variables and parameters that are associated with it. And grid handles the particle inside grid and everything related with the electromagnetic fields. There is also algorithms and helpers which have like different mathematical operations and functions that are used across all the code. So these are the common functions. Okay, before starting implementing the code, it was necessary to create a code profiling in order to understand how it was performing from a time consumption perspective. So we use cprofile and obtain this code profile. We analyze it, and we have 2 main functions that were consuming the majority of the time. The first one is read laboris kick, and the second one is current deposition. Actually, read laboris kick is split into different sub-functions. So while current deposition is just one big function which has a lot of mathematical operations, some of these are vectorized. So we converted some of these into for loops, and that's like our base to start the parallelization. All the experiments were run on Comparative supercomputer at the National High Technology Center of Costa Rica. This supercomputer has 4 different architectures. We use 2 of them, the many-core architecture and the multi-core architecture. The many-core uses Intel Xeon Phi that runs on 1.3 gigahertz, and the multi-core architecture uses Intel Xeon Volt at 3.0 gigahertz. The table 1 shows the software configuration, and the table 2 shows the Python Pig parameters. Basically, we run 3 different types of simulation with 100,000 particles, 200,000 particles, and the last one, 400,000 particles. For implementing the code into Python Pig, we use multiprocessing, which is a Python native library, so we didn't have to make any external package installation. The map function of multiprocessing allows only the function and the iterable, so it was required to create global variables in order to handle the usage of these variables in the overall operation. There is also the requirement to use multiprocessing arrays for this. And we use, instead of the map function, there is an enhanced version which is called IMAP, and this is for large iterables. So we use IMAP instead of map. And a chunk size in order to split the data into chunks, and this the intention is to improve the efficiency of the function. PyNB did require external package installation. From the for loops, it was kind of easy to implement the PyNB changes because it required a small number of changes, and it also requires the usage of PyNB shared arrays. For TorPy, it also requires external package installation. The map function for TORPy, it actually allows the usage of multiple variables, so it was not required to create global variables as in multiprocessing. And we also use the chunk size here, and the start function as I was mentioning at the beginning. So after the code was transformed, it was necessary to understand a correct chunk size value, because in the documentation there was like no specific, there was like no specific way on how to select this value. It only said that you can use large value, that actually very large value can affect your performance. So in the case of multiprocessing, we use different values and the behavior was always very similar. So we use the default value, which is 1. And for TORPy, we noticed something interesting, that the default value of 1 was actually having a higher execution times than using some other different random value. So we removed this default value and created this TORPy reduced results, from where you can see that actually the 500 chunk size value is the one with less execution time. Based on this, we got the strong scaling results, from where you can see that multiprocessing is the best, has the best performance with less execution time and better scalability. Multiprocessing also has a good performance, but the scalability is not as good. And in the TORPy's case, we noticed that it was having an unexpected behavior. As we increase the number of cores, actually the execution time was increasing, so this was not expected. For the multi-core case, multi-core processor, we did a similar analysis with the chunk size. The multiprocessing had the same behavior by changing the value of the chunk size. We got basically the same performance. So we maintained the default value of 1. And for TORPy's case, we also got the same behavior, that when using the default value of 1, we are having higher execution times than using our different values. In this case, we reduced the default value, and we noticed that also using a chunk size value of 500, it was having the best results. Actually, when you use a higher number of that, you get like actually the unexpected behavior on the simulation with increasing time execution results. Based on this, we obtained the strong scaling results. Again, PyMP was the tool with the best performance. Multiprocessing and TORPy also had a kind of a good performance, but the scalability for TORPy and multiprocessing was not as good as in PyMP. For the multi-core case, we proceed to obtain the weak scaling results. Basically, on the weak scaling, what you are doing is, as you increase the number of cores, you are also increasing the number of particles. So what you will expect is to obtain a flat line with slope equals to 0 from execution time, because you will put that's like the perfect case when you see the execution time being like flat. PyMP got the best results. As a second case, multiprocessing actually had really good results using 8 or less workers. And TORPy initially got good results, but as you increase the number of cores, it was increasing a lot, so the scalability was not very good. We use a fork case, which is NumPy. NumPy is a just-in-time compiled alternative. The only issue with NumPy is that you are not able to select the amount of cores that you want to use. So you simply insert the parallel instructions and it runs. The multi-core processor got very good results actually, but the best results were presented in the many-core case with the 400,000 simulation. In this case, we had an improvement of performance of around 43%. So as final remarks, I would like to mention that particle in cell simulations require large computational resources. In the physics, as you increase the granularity of the simulations, you obtain more realistic results, but you also increase the computational resources, and that is important there. Python is a growing programming language with support and libraries for scientific computing and HPC. PyMP obtained the best performance in comparison to multiple processing, and TorquePy. TorquePy didn't escalate properly in the many-core processor, and Numba is an excellent option to use depending on how the code was implemented and how you want the parallelism to be. Thank you very much for your attention.
Thank you.